students, welcome back. In this video, we see all the 2-mark questions of complex numbers. If given 1 plus I, 1 to 1 plus 2i, product of 1 plus ni is equal to x plus iy, prove that 2 into 5 into 10 into etc. 1 plus n square is equal to x square plus y square. So for this, let us write first what is given. Take the modulus on both the sides. Modulus of 1 plus I into 1 plus 2i goes on up to 1 plus ni is equal to modulus of x plus iy. This modulus of z1 into z2 into z3 can be written as up to zn can be written as is equal to modulus of z1 modulus of z2 up to modulus of zn. So using this property, we are going to separate the modulus here. This is modulus of 1 plus I, modulus of 1 plus 2i goes on up to modulus of 1 plus ni is equal to modulus of x plus iy. Modulus, we know modulus is root of real part square plus imaginary part square. So 1 square plus 1 square. So the modulus for this will be root of 1 square plus 2 square, and it goes on up to nth term, that is the root of 1 square plus n square, which is equal to root of x square plus imaginary part square, that is y square. So this is root of 1 plus 1, 2, root of 1 plus 4, 5 goes on up to this is root of 1 plus n square. Now this is equal to right hand side x square plus y square. So squaring on both the sides, we get 2 into 5 into goes on up to 1 plus n squared is equal to the given question. What is given? 2 into 5 into etc. will be is equal to x square plus y square, hence proved. The next question, simplify. A term is given. So first we consider the first term of the given question. So that is 1 plus I divided by 1 minus I. We simplify first. This is equal to 1 plus I divided by 1 minus I. Take the conjugate of the denominator. So multiply by 1 plus I by 1 plus I, which is equal to 1 into 1 is 1 plus I plus I squared divided by 1 square minus I squared. Now this is equal to, we know that I is equal to root of minus 1, I square is equal to minus 1, I cube is equal to minus I, and I power 4 is equal to 1. So using this, we are going to simplify the given question. Now this is equal to 1 plus 2i, I square is minus 1 divided by denominator 1 minus of I square is minus 1. So this gives us is equal to 2i divided by 2, which is equal to I. Therefore, the next term, 1 minus I divided by 1 plus I is the reciprocal of the first term, and therefore it can be written as 1 by I. Denominator, this is 1 by I into I by I, which is equal to I by I square minus 1, which is equal to minus I. Therefore, coming to the question, 1 plus I divided by 1 minus I the whole cube minus 1 minus I divided by 1 plus I the whole cube is equal to I cube minus of minus I the whole cube, which is equal to minus I plus minus into minus is plus I cube. So again, this is equal to minus I, which is equal to minus 2I. The next question, find the least positive integer n such that given 1 plus I by 1 minus I whole power n is equal to 1. So let us consider the term inside the bracket. So consider 1 plus I divided by 1 minus I. Like the previous problem, we take the conjugate of the denominator into, so we take this is equal to 1 plus I divided by 1 minus I into 1 plus I divided by 1 plus I. Now this is equal to 1 plus I plus I plus I squared divided by 1 square minus I square, which is equal to 1 plus I is 2i, I square is minus 1 divided by 1 minus of I square is minus 1, so becomes 1 plus 1. Now this is again is equal to 2i divided by 2, which is equal to I. Therefore, from the given question, 1 plus I divided by 1 minus I whole power n is equal to 1 implies I the whole power n is equal to 1. We know that I power 4 is equal to 1. Therefore, when n is equal to 4, the value of 1 plus I by 1 minus I whole power n is equal to 1. Therefore, n is equal to 4 here. The next question, obtain the Cartesian form of the locus of z is equal to x plus I in z plus I is equal to z minus I. So, given z modulus of z plus I is equal to modulus of z minus I. Let us take, let z is equal to x plus iy. Now substitute for z as x plus iy, we get x plus iy plus I, x plus iy plus I is equal to modulus of x plus iy minus I. Now separate the real and imaginary terms here. So this will be x plus I into y plus 1 is equal to modulus of x plus I into y minus 1. Now squaring on both the sides we get this is equal or we taking the modulus on both the sides we get root of x square plus real part the whole square plus imaginary part the whole square, that is y plus 1 the whole square is equal to modulus of x square plus y minus 1 modulus of x square plus y minus 1 the whole square. So squaring on both the sides we get this is x squared plus y plus 1 the whole squared is equal to x squared plus y minus 1 the whole squared. Now x squared on both the sides goes off. Now next we get here y plus 1 the whole square is y squared plus 2y plus 1 is equal to y squared plus minus 2y plus 1. So y squared, y goes off, we get 4y is equal to 0, which implies y is equal to 0. Y is equal to 0 is the equation of x-axis. Therefore, locus of z is y is equal to 0. Simplify this term first. This is equal to 2 into 1 is 2. We write the real parts separately first, minus 3i the I squared into multiply the next terms, that is 3 imaginary terms. So I get here plus I into 3 minus I into 2. Now this is equal to I square we know is equal to minus 1. So substitute I square as minus 1. So we get 2 plus 3 plus I into 1, or this is equal to 5 plus I. So we have got z is equal to 5 plus I. Now we find z inverse. Z inverse is equal to 1 by z, which is equal to 1 by 5 plus I. Take the conjugate of the denominator, and this is equal to 1 by 5 plus I into 5 minus I divided by 5 minus I. Now this is equal to 5 minus I divided by 5 squared minus I squared. This is equal to 5 squared minus I squared, which is equal to 5 minus I divided by 5 squared is 25. I squared is minus 1. Minus of minus 1 is plus 1, which is equal to 5 minus I divided by 26. We are asked to prove Z inverse is equal to real part separately, imaginary part separately. Therefore, we write Z inverse is equal to 5 by 26 minus I by 26. The next question, given Z1, Z2, Z3, show that 1 plus Z2 plus Z1, Z2 plus Z1, Z3. So let us first write what is given. Given values of Z1 is equal to 3, Z2 is equal to minus 7i, and Z3 is equal to 5 plus 4i. Now finding the LHS first. LHS is Z1 into Z2 plus Z3, which is equal to Z1 is equal to 3 into minus 7i plus 5 plus 4i. Now this is equal to 3 into 5, real part is 5, minus 7i plus 4i gives us minus 3i. Multiply with 3 inside, we get 15 minus 9i. This is the LHS. Now coming to the RHS, RHS is Z1, Z2 plus Z1, Z3, which is equal to Z1 is 3, Z2 is minus 7i, plus Z1 is 3 into Z3 is 5 plus 4i. Now this is equal to minus 21i plus 15 plus 12i. Now this is equal to, the real part is 15, minus 12i plus 12i minus 21i gives us minus 9i. Therefore, from 1 and 2, we can write from 1 and 2, LHS, that is Z1 into Z2 plus Z3 is equal to Z1, Z2 plus Z1, Z3. Next question is very simple and important. Prove that the real part of Z is equal to Z1, Z plus Z bar by 2 and imaginary part is Z minus Z bar by 2. So let us first take given. Let us first write let Z is equal to X plus IY. Therefore, Z bar the conjugate can be written as is equal to X minus IY. Now adding Z plus Z bar will be is equal to X plus IY plus X minus IY, which is equal to 2X. Or Z plus Z bar by 2 is equal to X, where X is the real part of Z. X is the real part of Z and Y is the imaginary part of Z, and this gives us this is equal to real part of Z. So we have proved the first part. Coming to the second part, take Z minus Z bar, which is equal to X plus IY minus of X minus IY. So this is equal to X gets cancelled. This is equal to 2IY. Now this is Z minus Z bar by 2I is equal to Y. Here Y is the imaginary part of Z. Therefore we can write imaginary of Z is equal to Z minus Z bar by 2Y. State and prove that we have modulus of Z1 plus Z2 is less than or equal to modulus of Z1 plus modulus of Z2 we have to prove here. So coming to the proof, let us take modulus of Z1 plus Z2 the whole squared first. We know that modulus of Z square is equal to Z bar. So using this, we can write this can be written as Z1 plus Z2 into Z1 plus Z2 the whole bar, considering this as Z. Now this can be again written as this is equal to Z1 plus Z2 into Z1 bar plus Z2 bar. Now again this is equal to multiply the terms inside the bracket. We get Z1 Z1 bar plus Z1 Z2 bar plus next Z2 Z1 bar plus the next term Z2 Z2 bar. Now this is equal to this term Z bar can be written as modulus of Z square plus these two terms we combine together, write it as Z1 Z2 bar plus Z1 Z2 bar the whole bar plus Z2 Z2 bar can be written as modulus of Z2 squared. What that Z bar is equal to modulus of Z. That is what we have used here. Next, we are using this term, this Z1 bar, Z2. Here for Z1, there is only one bar. Z2, we have double bar here. So we know that Z double bar is equal to Z. Z double bar is equal to Z. We are using these two results here. Now, this can be again written as this is equal to modulus of Z1 squared. This can be written as modulus of Z1 squared. Now the property what we have proved, Z plus Z bar can be written as is equal to 2 times real part of Z. So this is of the form Z plus Z bar. Z is Z1, Z2 bar. So this can be written as plus 2 times real part of, in the place of Z we are having Z1, Z2 bar plus modulus of Z2 square equal to, we know that real part of Z is less than or equal to modulus of Z. The real part of Z is less than or equal to modulus of Z. So in this state, I'm going to give less than or equal to sign modulus of Z1 squared plus modulus must be given here. So I write 2 times modulus of Z1 Z2 bar plus modulus of Z2 squared. Now this is equal to modulus of Z1 squared. Now this is equal to modulus of Z1, Z2 can be written as modulus of Z1 into modulus of Z2. Since we know that modulus of z bar is equal to modulus of z plus modulus of z2 squared. Now this is equal to modulus of z1 plus modulus of z2 the whole square. Now both the sides, this is left hand side is modulus of z1 plus z2 the whole square is equal to modulus of z1 plus modulus of z2 whole square. Therefore, taking square root on both the sides, it can be written as modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. Hence proof. The next question is another important and a simple question. Here given modulus of z is 2, list 3 is less than or equal to modulus of z plus 3 plus 4i less than or equal to 7. So I'm going to use the result here, whole modulus of z1 minus modulus of z2 is less than or equal to modulus of z1 plus z2 less than or equal to modulus of z1 plus modulus of z2. Using this property, we can simplify the given question in a single line. So let me take here, let z is equal to z1 is equal to z, and I'm going to take the second term 3 plus 4i as z2. So here let me take z2 is equal to 3 plus 4i. Now the modulus of z1 will be is equal to z modulus of z. Similarly, modulus of z2 is equal to modulus of 3 plus 4i, which is equal to root of 3 squared plus 4 squared is equal to root of 9 plus 16 root of 25, which is equal to 5. Modulus of 3 plus 4i less than or equal to the given question, that is z plus 3 plus 4i less than or equal to modulus of z plus modulus of 3 plus 4i. Now this again implies modulus of z given in the question. So we are going to use that here. So this is whole modulus of z is 2 minus modulus of 3 plus 4i. We have found it is 5 less than or equal to modulus of z plus 3 plus 4i less than or equal to modulus of z is again 2 plus modulus of z plus 4i, which is equal to 5. Now this is modulus of minus 3 gives us 3 here less than or equal to modulus of z plus 3 plus 4i less than or equal to 2 plus 5, which is equal to 7. This I sin theta in the form of a plus ib is another simple question. We can write e power cos theta plus I sin theta, which is equal to e power cos theta into e power I sin theta. We know the Euler's formula, e power I theta can be written as is equal to cos theta plus I sin theta. So here we are going to use the Euler's formula, which can be written as this is equal to e power cos theta e power I sin theta. In the place of theta, we have sin theta. Therefore, it can be written as cos of sin theta plus I sin of sin theta. Now, I want it in the form of a plus ib. So, the real part here will be is equal to, the real part is equal to e power cos theta into cos of sin theta. And the imaginary part will be is equal to e power cos theta into I sin of sin theta. When we want to write it in the form of a plus ib, so it can be written as this is equal to e power cos theta into cos of sin theta plus I into e power cos theta into sin of sin theta. In this question, show that the three given points are the vertices of an equilateral triangle. So in this Argand diagram, taking the real values along the x-axis, construct the triangle and show that it is equilateral here. So let us first take the given points as the three complex numbers. Z1 is equal to 1, Z2 is equal to minus 1 by 2 plus I root 3 by 2. And the third number as Z3 is equal to minus 1 by 2 minus I root 3 by 2. Using the distance formula, we are going to find the length of the given sides. So length of sides of the triangle can be written as modulus of the first side Z1 minus Z2 is equal to modulus of 1 minus of 1 minus of minus 1 by 2 plus I root 3 by 2, which is equal to modulus of 1 plus 1 by 2. 1 plus 1 by 2 gives us 3 by 2 minus I root 3 by 2. Modulus can be written as this is equal to root of 3 by 2 the whole square, which is 9 by 4, plus root 3 by 2 the whole square, which is equal to 3 by 4. Now simplifying this, we get is equal to root of 12 by 4, which is equal to root 3. This is 1. Next, coming to the second length, Z2 minus Z3 will be is equal to modulus of Z2 is minus 1 by 2 plus I root 3 by 2 minus Z3 is minus 1 by 2 minus I root 3 by 2, which is equal to modulus of minus 3 by 2, 2 gets cancelled. We get a root of imaginary part is just root 3 whole square, which is equal to 3, which is equal to root 3. This is equation number 2. Next, the third side, Z1 minus Z3 will be is equal to modulus of 1 minus of minus 1 by 2 minus I root 3 by 2. Now this is equal to root of 3 by 2 whole square. 1 plus 1 by 2 is 3 by 2 the whole square plus I into root 3 by 2. So that is root 3 by 2 the whole square, which is equal to root of 3 by 4, root of 9 by 4 plus 3 by 4, root of 12 by 4, which is equal to root 3. So from 1, 2 and 3, we see that all the three length of the three sides are equal. Therefore, we can say the points form an equilateral triangle. Find the square root of 6 minus 8i. We know the formula to calculate the square root. Root of a plus ib is equal to plus or minus root of modulus of z plus a by 2 plus I b by modulus of b into root of modulus of z minus a by 2. Using this formula, we are now let us find the square root of 6 minus 8i. Let z is equal to 6 minus 8i, where here we can take a is equal to 6 and b is equal to minus 8. First, let us find what is modulus of z. Modulus of z is equal to modulus of 6 minus 8i, which is equal to root of 6 square, that is 36, plus minus 8 the whole square, which is equal to 64, is equal to root of 100, which is equal to root of 10. Now coming to finding the square root of the number 6 minus 8i is equal to plus or minus, apply the formula here. So we get the whole root of modulus of z is 10 plus a is 6 divided by 2 plus I into b is minus 8 divided by modulus of minus 8 into root of 10 minus 6 divided by 2. Now this is equal to plus or minus root of 16 by 2, which is equal to 8, plus here modulus of 8 is nothing but 8. So 8 get cancelled here. So we get the minus sign. So minus I into root of 10 minus 6. 6 by 10 minus 6 is 4. 4 by 2 gives us 2. Now this is equal to plus or minus. For root of 8 is nothing but 2 root 2 minus I into root 2. So square root of 6 minus 8i is equal to plus or minus 2 root 2 minus I root 2. Obtain the Cartesian form of locus of z. We have seen a previous problem, right hand side. Z minus I was given in this problem. Z minus 1 is given here. So let us do the problem by the same procedure by taking let z is equal to some x plus iy. So writing the question modulus of z plus I is equal to modulus of z minus I. We are asked to find the locus. So this gives modulus of x plus iy plus I is equal to modulus of x plus iy minus 1 here in this question. So minus 1. So this is again can be simplified x plus I into y plus 1 is equal to modulus of x minus 1, writing the real part, plus iy. Now taking the modulus, this gives us root of x square plus y plus 1 the whole square. Right hand side, this is root of x minus 1 the whole square plus y square. Real part square plus imaginary part square. Now squaring on both the sides, we get the equation as x square plus y plus 1 the whole square is equal to x minus 1 the whole square plus y square. Expanding the equation, x square plus y square plus 2y plus 1 is equal to right hand side x square minus 2x plus 1 plus y squared. So here both the sides y squared, x squared gets cancelled. We get the equation 2y plus 2x, 1 on both the side is equal to 0, or x plus y is equal to 0, 0. The next question, simple question, given sigma n is equal to 1 to 12, I power n is equal to, first let us see, I plus I square plus I cube plus I power 4. This is equal to I plus I square is minus 1, I cube is minus I power 4 is 1, which gives us is equal to 0. This is I power 1 plus I power 2 plus I power 3 plus I power 4 plus I power 5 plus I power 6 plus I power 7 plus I power 8 plus I power 9 plus I power 10 plus I power 11 plus I power 12. All these terms, these first four terms, we get 0. I power 5 is I power 4 into I power 4 into I power 4 I squared, I power 6 is I squared, I power 7 is I cube, again I power 8 is I power 4 whole squared. So all the terms are of the form, this is equal to 3 times of I plus I squared plus I cube plus I power 4. So this is equal to 0. Another simple problem, if z is equal to x plus iy, we find what is real of 1 by z. So given z is equal to x plus iy. So real part of z we have to find. Let us first find what is 1 by z. 1 by z is equal to 1 by x plus iy. So multiply by the conjugate of the denominator, we get x minus iy divided by x minus iy, which is equal to x minus iy divided by x square minus I square y square. I square is minus 1. So we get the denominator as x square plus y square, which is equal to x divided by x square plus y square. We separate the real and imaginary parts, plus I into minus y divided by x square plus y square. We want the real part of 1 by z. So the real part of 1 by z is equal to x by x square plus y square. We have seen a similar type of question. We are going to use the formula here, property here, whole 2. Here we take let z is equal to, let z1 is equal to z and z2 the number is equal to 6 plus 8i. Now modulus of z1 will be is equal to, given in the question, modulus of z is equal to 2. Therefore, modulus of z1 will be is equal to 2. Modulus of z2 will be is equal to root of 6 square plus 8 square, which is equal to root of 36 plus 64, which is equal to root of 100 is equal to 10. Now using this property, we get whole modulus of z1, that is 2, minus modulus of z2 is 10, less than or equal to whole modulus of z1. z1, this must be written as how it is given in the question. So z plus 6 plus 8i less than or equal to modulus of z1 is nothing but is equal to 2 plus modulus of z2 is 10, which gives us modulus of 2 minus 10 is equal to minus 8. Modulus is given, so we get 8 less than or equal to modulus of z plus 6 plus 8i is less than or equal to 12, and hence proved.